Alright, ladies and gentlemen, welcome to the stream. Alright, first we gotta draw out our circuit. We got our independent voltage source right here. Now this circuit is going to contain an inductor and a capacitor. And then we're gonna have a couple switches. We have a switch here, a switch here. Okay, we got a capacitor here. Bada bing, bada boom. And then we have another resistor right here in parallel with that capacitor here. Over here we have our inductor. Just like that, okay. Alright, so this is the circuit we're gonna be analyzing. Let me go ahead and give some parameters, some variables here. We're going to define our resistors. Let's see, we got positive, negative. We're going to define this as just V. We have what? R1, R2, C, L. Okay, so R1, R2, we have C, and we have L. Inductors are really defined by the current flowing through them. Capacitors are really defined by the voltage across them, Vc of T. Because of the way that they store energy, a capacitor stores energy in an electric field, and this has a relationship to voltage. And then an inductor stores energy in a magnetic field, and this has a relationship to the current flowing through it. Okay, so at T equals 0, right, this is going to close at T equals 0. All right, and then at T equals T is going to open. So when T equals T, and again when T equals T, this is going to close. T equals T. Okay, again, some arbitrary value of time. I don't think it even specifies. Okay, so let's hop into the problem. Let me explain a little bit what's going on. Until time T equals 0, both switches are open, and the circuit is initially at rest. We don't have no voltage. We don't have no current stored up, or no current flowing, no voltage stored up, except in the resistors, which we have a voltage divider, right? Two resistors in series, we're going to have a voltage divider, and this is defined by the voltage divider relationship, which you could define in other ways, but it's so common that it's worth remembering the voltage divider relationship. So both switches are open, and the circuit is initially at rest for T equals 0. Okay, at T equals 0, switch S1 is closed, but S2 stays open. After a very long time, capital T, S1 is open and S2 is simultaneously closed. What is Vc of T during I guess we'll write it, during 0 T. Okay, so that's what we're about to define right now. RC circuit. So what we're going to do is we're going to convert into our Thevenin equivalent right now, because really we just want an RC circuit where we have one resistor in series with our capacitor. So to convert that into the Thevenin equivalent, we're going to look at directly across the capacitor. Yeah, I'm going to need the voltage. Okay, so we're going to say that V Thevenin equals, and as I said, you know, here comes the voltage divider relationship just right off the bat like that, boom, bang, is that we just want the voltage across this resistor because it's in parallel with this capacitor, therefore the voltages are equal. Okay, Kirchhoff's voltage law. The voltages around this loop sum to 0. Okay, that's Kirchhoff's voltage law, KVL. KVL. Put that in letters so we see it, perceive it, and think about it a little more. So now, in order to define the voltage across this resistor here, we're going to use the voltage divider relation. Okay, so this is just simply going to be the input voltage V. Since we're going across R2, this is going to be in the numerator, R2, divided by R2, the sum of R2 and R1. Okay, so that's our Thevenin equivalent voltage. Now we got to define the Thevenin resistance. Thevenin resistance, R sub TH equals, okay, so again, it's the resistance perceived by the capacitor itself. This voltage here, because it's a voltage source, it's going to become a short. If it were a current source, it'd become open. Just draw another model. We're going to short that. We're going to have this resistor here. That's going to go to the capacitor. We're going to have this resistor here. Just like that. We want to know the resistance R Thev perceived right here. Okay. So that's pretty much what we have, and then we'll put ground for reference. So if this is what we have, then this just means that these two resistors are in parallel, okay? It's really going to be is 1 over R1. This is the way that you add resistors in parallel. 1 over R1, 1 over R2, and then this is all under 1, which we can write like that. So this is going to equal R2. It's going to be like, and then we'll just reverse it. So it's going to be like this, ultimately. R1 plus R2. Okay, so that's what R Thevenin actually equals. Okay, like that. So we have V Thev, we have R Thev. Okay, so now let's draw our new circuit. It's just our simple RC circuit. This is what we wanted. Which the Thevenin equivalent circuit looks exactly like this. It's just a source with a resistor in series, and then our output, we have our load, I guess we can consider it, is our capacitor. So we just want to define the voltage across VC of T. Positive, negative, this is V Thevenin, and this is R Thevenin. Just like writing our first order linear differential equation. And this is going to require the constitutive law, the capacitor's constitutive law. All right, it's going to be like that. Constitutive, cross your T's, dot your I's, constitutive law. For the capacitor is going to be this. We're going to define it by IC for sure. So this is going to equal C times the derivative of the capacitor voltage with respect to time. So it's going to be like that. That's our constitutive law, for the current of the capacitor. For that, we're going to look at this node right here, and we're just going to call him VC. That's our node, and then we'll put ground for reference. Need to know where our ground is. Okay. So now we're going to use node analysis. And we're just going to say, remember Kirchhoff's voltage law. This is like Kirchhoff's current law. Okay, Kirchhoff's current law. That means the sum of the currents entering a node equals 0. C plus, we'll say IS from the supply equals 0. Okay, let's define this by the voltages. It's going to be, okay, constitutive law. So we're going to have C times the derivative of the voltage across the capacitor with respect to time plus the current in that direction is going to be defined by the voltage across the capacitor minus the supply voltage, or the Thevenin equivalent, the Thevenin voltage, divided by this resistance, R Thevenin. All right, we're going to say equals 0. Okay, so we just define the currents by the voltages. Since we have a drive, we're going to have a particular solution. Do that now. We're going to isolate the derivative by dividing by C. So the derivative of the voltage across the capacitor with respect to time plus the particular solution is going to lead us to this VC over RTH equals, right, if we separate the numerators, or like separate this fraction into the numerator over this denominator minus this numerator over this denominator, and then we add VTH over RTH to the other side. VTH, RTH, that's just Thevenin. RTH is obviously going to cancel, and our particular solution, which we'll denote as VCP, we'll denote as VCP, particular solution of the capacitor voltage equals VTH. Okay, now the homogeneous solution is a little different. dt plus VC times RTH. Our capacitance times our Thevenin resistance is going to look like this. And then we'll draw ground for reference. Okay, it's going to look like that. All right, we're not going to have our VTH here. We're not going to have the supply. We don't want to drive. What the All right, so our homogeneous solution, we're going to assume that VCH equals a form like this. All right, so we're going to plug in this this solution to the problem. So we're going to say the derivative of, I just plugged in this. I plugged in this everywhere there was a VC. Okay, everywhere there was. All right, so as I said before, okay, we're going to have A times SESTTH. And I simply just took it out of the numerator. A, and that leaves us with S. This side is going to leave us with 1 over C times RTH. Okay, now we're going to take everything inside the parentheses and equivalent that to 0. And so that's just going to mean S equals 1 over C times RTH. VCH. Oh, just moments before. Okay, so it's just going to be VC. We're just going to say VC of 0 equals, it's going to be our Thevenin voltage. If you plug in 0 here, you're going to have 0 in the exponent, and then what is a variable to the power of 0? It's just 1. Okay, so if that's 1, we simply have VC of 0 equals A, and then that's just going to equal V, our Thevenin voltage. Because think about it, as soon as this closes, our voltage divider is going to give us the voltage across this resistor, which we defined as our Thevenin voltage. So our Thevenin voltage, this being in parallel with our capacitor, is going to be the same voltage across the capacitor. That's how. Okay, so our final solution is going to look something like this. So VC of t equals VTH, our particular solution, VTH times e to the power of negative t divided by our THC. So we just got to go ahead and plug everything in. It's a bit tedious, but I mean, that's what it's asking for. So VTH is going to be V times R2 over the sum of R1 plus R2. All divided by R1, R2, C. Yeah. Actually, this isn't what we have. So at t equals t or after t, this switch is actually open. So we know we're no longer a part of the resistive circuit. That is true at t equals t. So we'll come down and draw this right here. All right, just like that. Ground for ref. We're looking for VC, so we're going to use this. So let's put the constitutive law, VC, with respect to time, plus IL. We can define IL by the integral. We're going to say, so it'd be 1 over L. This is the constitutive law for the inductor. 1 over L times the integral of the voltage across the inductor, which is also VC. So that's, okay, I'll give it some space. So C times dV, second derivative of C with respect to time. You don't see that yet? Okay. That's going to be plus, we derive this function, so we get rid of the integral 1 over L times VC equals 0. All right, so look how we have VC, and then we have the second derivative of VC. This is what makes a second order linear differential equation. Okay, so we have this 1 over LC times VC equals 0. Okay, so in this scenario, if we have a first order linear differential equation or a second order linear differential equation, regardless, we're going to need the particular solution and the homogeneous solution. The particular solution is applicable if we have a drive, okay? In this case, we don't have a drive, so we're only going to need to find the homogeneous solution. So we're going to assume a form for VC equals this homogeneous. We're going to assume a solution of the form A times e to the power of st. It's going to lead to A times A and then be e to the power of st equals 0. All right, so we're just going to say that s equals plus or minus the square root of 1 over LC, okay? Because we're setting this right here in the parentheses equal to 0. We set that equal to 0 itself, and this is the solution that it leads to. So now we have two possibilities, okay? So this is going to lead us to two exponential functions. Here, to make things more simple so that we can follow along with ease, we're going to say that omega naught equals the square root of 1 over LC. In this case, we're going to say that VC of t equals this coefficient A1 multiplied by e to the power of omega naught t. Yes, okay, and then we're going to say plus this some arbitrary or some coefficient we haven't defined yet. A2 is different than this one though. A2 times e to the power of negative omega naught t. Okay, so we have s squared plus 1 over LC. So we need s squared equals the square root of negative 1 over LC. And that's what j equals. J equals the square root of negative 1. That's an imaginary number. Okay, that's j omega naught t. And then we're going to have negative j omega naught t. Okay, we're not quite there yet. So the Euler relation is e to the power j, we'll call it theta, equals cosine cosine, just theta. Yeah, just cosine theta plus this imaginary times sine of theta. Okay. So now we're going to write this as this. Vc of t equals k1. We're just going to convert the coefficient to k, okay, to make some distinction between the exponential function and the trigonometric function. Times cosine. Yes. Okay, so this is accurate. This is accurate. Reflecting on our two unknowns. We have two unknowns, therefore we need two equations in order to solve our two unknown variables. Down real quick so this makes more sense. IC equals C times the derivative of VC with respect to time. Okay, that's our constitutive law. We can get our second equation by deriving this and multiplying by C. So we can say that IC of t equals, as the derivative of cosine is negative sine. The derivative of so implicit differentiation is just the derivative of the inside function multiplied by the derivative of the outside function. A1 times omega naught. The derivative of cosine is negative sine. We have the negative sine. And then everything in the function stays the same, just like that. So we just had to pull the derivative of the inside function out, multiply it by the derivative of the outside function, and that's implicit differentiation. Plus k2 omega naught. Again, do implicit differentiation, and then the derivative of sine is just cosine. Cosine omega naught t. Okay, so VC of 0 equals, but first we got to do this. Okay, V thev, that is true, equals. So now we got to plug in 0 for t, okay, because VC of 0, that's our independent variable. Wherever we plug in 0, or whatever variable we plug in 0 for, we got to plug it in everywhere. Okay, times 0 is 0, cosine of 0 is 1. So you just have k1. Go IC of 0. At t equals 0, there is no current. Okay. So it's just 0. It's just 0. Therefore, k2 is 0. K2 sine. Okay, so now our final solution is this. VC of t equals V of omega naught t. Okay, V Thevenin is, okay, so this is our actual answer. Equals V Thevenin, which is V multiplied by R2, R1, square root of 1, right? We defined omega naught earlier as the square root of 1 over LC times, so this multiplied by, we want to establish like some sort of origin. So we're going to say T is our origin. The capital T is our origin. And in order to establish this mathematically, we're going to say T minus T. All of that within the cosine. This is our final answer. Follow me if you want to see more content like this. So I really appreciate y'all being here. I hope you have a wonderful rest of your day. God bless.